All right. Welcome, everyone. My name is Edouard Clément. I'm the Executive Director at the Energy Modeling Hub. So for those of you that are less familiar with our work, so we are a pan-Canadian consortium of universities and stakeholders that works on the open modeling tools and approaches. Our role is to develop different sets of open tools and data sets and also convene the community of energy modelers, researchers, and decision makers. We develop and maintain a suite of tools. You'll learn about some of those today and data platforms. So feel free to visit our website, www.cmeemh.ca, to learn more about our activities and tools. And we're glad to have you today with us for this webinar on a new tool that we were just releasing called PRAS, the Probabilistic Resource Adequacy Suite. The question behind it is easy to pose, but difficult to answer. Is the grid ready? So PRAS stress tests power system across thousands of simulated conditions: generator and transmission outage, variable renewable outputs, shifting demand, and the constraint of resource like storage and hydro. It gives you a full picture of where and when a system might fall short through regional balance assessments, hourly outage data, congested interface, identification, global reality metrics, and a map visualization and shortfalls of congestion. So within our M3 suite of tool, we have a tool called Copper and Silver that handle capacity expansion and production costs, but they couldn't really tell us whether a system is actually reliable. So PRAS tried to fill that gap and let us speak directly to the metric utilities and system operators can care about the most. So today we'll demonstrate how PRAS works and how it applies to real policy and planning questions. We also cover PRAS linkage, the Python preprocessing bridge that connect coders and our models output to PRAS. So to lead us through all of this, we have the pleasure to have with us our own Bipasa Agrawal, which is a modeling specialist and software developer at SESIT, UVIC. Bipasa holds a bachelor in computer science from University of Victoria and works at the intersection of software engineering and energy system modeling. She built Python tools for visualizing energy networks and optimizing energy flows. She contributed significantly to the coders database, and made refinement to the Silver models that meaningfully improve its efficiency and performance. And today she will present us this exciting tools called PRAS. So Bipasa, over to you. So during this webinar, you can use the chat box to ask questions or the QA box as well. We'll try to answer some of them as you propose them, and we'll have time at the end also to answer additional questions with Bipasa. So Bipasa, over to you.
Amazing. Thank you, Edward. And good morning, good afternoon, good evening, everyone from wherever you're joining. And thank you for being here. And thank you especially if you're leaving the Argentina match today to be here. Today, I want to walk you through a project that sits right at the intersection of long-term power system planning and probabilistic reliability simulation. The project is called the PRAS Linkage Pipeline, and over the next hour, you'll understand what PRAS actually is, where our data comes from, how the pipeline works step by step, and what kind of real planning questions we can answer with it. And I'll start with the concepts first and then build towards more of the technical detail. Before I get started, I also want to say a quick thank you to Maddie Seattle, who's really helped me think through all of the different moving pieces of this linkage, and Jonas, who's also implemented the extreme weather configurations that we'll get more into a bit later in the presentation. Amazing. So let's start with the problem that we're actually trying to solve, because everything else flows from this as the electricity grid transitions. We're tiling coal plants, building wind, solar, expanding interprovincial transmission lines. The question isn't just will we have enough capacity, it's will we have enough reliable capacity even when things go wrong. And things go wrong constantly. Generators trip, transmission lines fail during storms, demand spikes to unexpected levels during cold snaps, heat waves. None of this is predictable for any given hour. So what we need to do is find a way to simulate all of this uncertainty across thousands of possible futures and ask, in how many of those futures does the grid actually fail to serve load, and by how much? And that's the question that PRAS is designed to answer. And that's why this linkage pipeline exists, to take our future planning data and translate it into something that PRAS can simulate. So before I get into the tools, let's talk about resource adequacy. Resource adequacy is the long-term ability of a power system to supply enough electricity to meet demand at all times. Adequacy is a planning question. So do we have enough generation and transmission over the course of a year? For a while, we answered this with deterministic methods. So assume your biggest generator trips, and you have to make sure that you have enough reserve capacity to cover it. Simple, but it doesn't quite capture the statistical reality of the program. Multiple generators can fail simultaneously. A drought can reduce hydro output for months. A heat wave can push demand up while also increasing generator failure rates at the same time. So probabilistic methods like PRAS capture all of that by running thousands of simulated samples and reporting across all of those. How often does the system fall short and by how much? And that's more useful for planning discussions than just a deterministic margin. So PRAS stands for Probabilistic Resource Adequacy Suite. It's an open source simulation tool developed by NREL, or I guess the National Laboratory of the Rockies now, and the lead developer is Scott Stephen. It's written in Julia, which is a high performance scientific computing language, and it's specifically designed for this kind of large scale Monte Carlo work. At its core, PRAS simulates a multi-region power system, hour by hour, across thousands of samples, and in each sample, it randomly draws equipment failure based on the generator and lines failure rates and simulates whether the remaining supply can meet demand in each region for all 8760 hours of the year. And it records any shortfall. So the aggregated statistics from all of those samples gives us the reliability metrics with confidence intervals. So let me walk through what PRAS actually models, because this is important for understanding everything we need to prepare. Firstly, our assets like generators, storage, etc. This covers everything from natural gas plants to nuclear, coal, biomass, wind, solar. Each generator has a nameplate capacity, a forced outage rate, which is the per hour probability of a generator or anything randomly failing, and a repair rate. For variable renewables like wind and solar, the available capacity varies every hour based on weather. So we also feed in like a 8760 hourly capacity factor value grid. Second, regions. PRAS regions are used to represent a collection of electrical buses that are just grouped together for resource adequacy assessment purposes. Power transfer between buses within a single PRAS region is assumed to take place on a copper sheet, which means that there's no intra-regional transfer limits or line reliability limitations considered. Third, transmission. PRAS models both individual lines between regions and also aggregated interfaces, each with a forward and backward capacity limit. Lines can also fail, they have their own outage rates. Any set of two regions can have at most one interface connecting them. And fourth, demand. Each region gets an hourly load time series, and all of this ends up in a single HDF5 file that PRAS reads. So PRAS is great for answering those big what if questions. What's the reliability benefit of a new transmission line? How much does a new generator actually improve our system adequacy? It also helps us pinpoint risk. We can see which regions and which times of the year are driving our shortfall risk, and we can use it to stress test the system against extreme events like major generator or transmission outages. So these are the four metrics that PRAS produces, and it's used frequently. LOLE, that's the expected number of hours per year that the system will experience a shortfall. So the industry standard for this loss of load expectation is about 2.4 hours per year or 0.1 days per year. And LOLE is a peak focused metric, which means that it's primarily driven by whether the system can meet the highest demand periods or not. The EUE, the expected unserved energy, captures like not just how often you fall short, but by how much load you fail to serve on average, which is measured in megawatt hours per year. A system could have a very low LOLE but a high EUE, meaning that shortfalls are rare, but they're catastrophic when they happen. EFC is the equivalent firm capacity, and that answers how much perfectly reliable, always available capacity is a given resource equivalent to. So this is how we credit new resources: wind farm, transmission lines, inadequacy planning. So it's calculated by running two scenarios and finding the capacity difference that produces the same LOLE or EUE. And finally, ELCC, the effective load carrying capability. This tells us how much additional load a resource allows the system to serve while maintaining the same reliability level. This slide just describes what PRAS inputs actually look like, because understanding the target format is what drives all of the pre-processing work we do. So the pipeline produces all of these as intermediate text files first, and then packages them up into a HDF5 file in one final step. The schema that we have to follow is pretty strict. Group names, data type, matrix dimensions, and they all have to match very closely. This brings us to a typical workflow and the focus of our work. It all starts with the data preparation. So we start from sources like capacity expansion models, which in our case, we're using our copper model, or just databases like coders, which need to be processed into the format that PRAS requires. And once that data is ready, we set up our model and run the simulations. After the runs are complete, we can dive in, analyze the results. And in terms of actually running PRAS, we invoke it through Julia scripts. The main one is called PRAS analysis, which runs the standard adequacy Monte Carlo and produces LOLE, UE, hourly shortfall results. And then there's the PRAS analysis EFC, which handles the equivalent firm capacity comparisons. So again, you give it a baseline and comparison. You need to have two scenarios for that, and you need to have run those already once, and then you run the EFC, and it runs a bisection search to find the EFC value. And again, the PRAS analysis ELCC does the same for the effective load carrying capability. The number of Monte Carlo samples is controlled by the PRAS sample settings in the scenario config file. We've run as few as 100 samples just for quick sanity checks, and as many as 100,000 for final results. For larger scenarios, these runs can take a while sometimes, so which is why we also have the pipeline also includes a Slurm batch script for running on high performance computing clusters. The outputs land in a PRAS output folder. That's general LOLE, UE text files, CSV of hourly shortfalls per region across all samples, and transmission utilization CSV, and a file flagging congested interfaces. I'll cover each of these when we get to the results interpretation slide. So like any tool, PRAS has areas where it excels and areas where we need to be a bit more careful. On the strength side, PRAS scales well to large, complex multi-region systems. It can handle thousands of generators and hundreds of transmission lines without performance issues. It explicitly models transmission congestion, which is critical for interprovincial adequacy studies. It's fully open source, transparent. Every assumption can be reviewed, and it's probabilistic, which means that it gives you the frequency and severity of shortfalls across a large sample rather than just a single pass-fail deterministic answer. On the limitation side, PRAS gets less accurate as you push towards very fine nodal granularity. Tools like Silver or dispatch models are more suited to true nodal level studies. PRAS is better at regional and zonal analysis, which is exactly what we're doing. Results are also sensitive to input assumptions, especially outage rates and demand forecasts. Poor input and even small changes in stuff like failure rates can lead to a bigger change in results. Let's turn to the data. So on one side, we have the coders, which is our database of Canada's current electricity system, which exists on the grid today, basically. And on the other side, we have the capacity expansion model. We use copper, which tells us what the future grid should look like after decades of investment. Copper gives us the current physical network, where the nodes are, how the lines are connected, where the different generators physically sit. And the capacity expansion model gives us the future capacity mix, how much wind, solar, gas storage, and new transmission will be built by like 2035, 40, 50, whatever your year is. And then our pipeline takes them and transforms them into a coherent PRAS model. However, our copper model currently, it doesn't have the architecture of the grid in the output. So it still uses coders to fill in that data, like the location of generators, which lines connect to different nodes, etc. So the challenge is that the output from copper and coders are not just plug and play with PRAS. You have a lot of incompatible data structures, complex tasks like generator mapping, demand distribution that need to be handled. So our solution for this is this automated pipeline. It's built to handle these complexities, which detects where the data is coming from, does network-based analysis for distributing demand and generation, and it also includes validation to catch errors before they make it into the model. Now let me walk you through the full pipeline from start to finish. Everything begins with the YAML config file in the scenarios folder. So that file specifies the year, the provinces, the data mode, and all the feature flags. So when you run the main Python file with a scenario name and an output folder, it reads that config and starts the pipeline. And then the steps run in order. We load data from coders or copper or whatever IRPs, and then it starts with the network processing where we figure out the topology. Then we process the generators, assign them to regions, handle VRE, hydro data, and then finally we also have a custom visualization suite. And then we have our subfolders in the output folder, PRAS input containing the model file and the .pras file and any debugging CSVs that were outputted, and then a PRAS output file containing the reliability results. So the first major step here is network preprocessing. So this model takes the coders or the copper transmission topology and builds a graph representation of the grid. So the main output of this step is the preprocessed data dictionary, which is a graph of all the nodes and the lines, the weight of each of the nodes, and the zone mapping. And then this dictionary is passed down to every downstream module. So here we have a very interesting challenge. We don't have access to node level demand data. In fact, for many provinces, we only have access to provincial demand data. And for these cases, we take the provincial level demand and distribute it to the nodes using our network importance factor. So how we do that is this method called node scaling. Node scaling tells us what fraction of provincial demand each node should carry based on its role in the network. So we calculate each node's importance for power transfer, which is called the betweenness, versus the capacity to receive power, which is called the degree. So for example, nodes with a higher degree, which is a higher capacity to receive power, but a lower betweenness, means that they have they receive power, but power doesn't necessarily route through them to go to other nodes, which means that they could be cities. And so they get a higher demand allocation. The other case is provinces like Alberta, for example. Currently, we have demand data that is a bit more disaggregated than just provincial level. AESO provides zonal data, and there are currently 42 zones in Alberta. So we take in the zonal demand and map which of our buses fall into which zone. And then we distribute this zonal demand to the nodes within each zone, again, using the same node scaling factor. So generator processing is the most complex step in the pipeline. This module takes all the generator records from coders or copper and normalizes them into the PRAS format. So firstly, we have the technology mapping. Coppers and coders use completely different technology naming conventions. Everything gets mapped through lookup tables and dictionaries. Secondly, the outage parameters. Each technology is assigned a failure probability lambda and a repair probability mu. So these are per hour probabilities in a two-state like Markov model. So these are different than what you would normally encounter, which are forced outage rates, but you can convert these into these forced outage rates and back again using this given formula and with mean time to repair and mean time to failure. We also have forced outage rates in our coders database for different technologies in case you want to access them. And third is the VRE capacity factors. For wind and solar, we read the MERA-based capacity factors time series, and then we use them to populate the hourly capacity matrix. The same weather year is used for all resources to make sure that we have realistic correlations. And then we also have the hydro modeling, which I will talk about a bit later in this presentation. So we have another interesting problem here. Our capacity expansion model copper sometimes assigns generators to nodes that don't currently exist, labeled like need to build. And these represent planned expansion which haven't been mapped to like the real network yet. So when that happens, this pipeline falls back to using the node scaling we discussed earlier to identify the most electrically important existing nodes and distribute those generators around them. So it works in different steps. First, it places firm capacity on the nodes that have the highest demand because firm capacity matters most for peak reliability. And then it places variable resources like wind and solar, where the ratio of the local generation to local demand is low, and preferentially places new capacity there. And this methodology does go off just demand and node scaling, so it can definitely be improved upon, and that's something that we plan to get to. Another challenge we face is that every wind and solar generator exists at a specific latitude and longitude coordinate in the coder's data. The MERA capacity factor data lives on a fixed geographic grid. So it's an array of grid cells across Canada. And this generator, the generator's coordinates often doesn't align exactly with any of our grid cell centers. So we run a 4-step matching algorithm. First, we check if the generator's coordinate match any grid cell exactly with a tolerance of something like 0.01 degrees. If yes, easy, we can just use that cell's profile directly. And if not, we calculate the distance from that generator to the nearest grid cell in the dataset. And then we apply a threshold check. If the data to the nearest cell is 100 kilometers or less, then we use that cell's capacity factor profile. But if it's more than 100 kilometers, meaning that we can't really find a nearby representative cell, we fall back to using the full nameplate capacity, and then we also flag it in the debug output for review. So hydro modeling. Modeling hydro in PRAS is something we struggled with for a while. So initially, I was modeling hydro generators as normal generators in PRAS, but what I should have been doing is treating them as storage generators in PRAS. So we split hydro into multiple types. The first is run-of-river hydro, which we call hydro run. It's modeled as a plain PRAS generator. So it generates based on its capacity factor and has no storing capacity because I think run-of-river plants generally don't store water between periods, and nothing changes here from the standard approach. As opposed to reservoir hydro, so like hydro daily, hydro monthly is modeled as PRAS generator storage. This means that PRAS tracks the energy level in the reservoir at every time step across the full 8760-hour simulation. So the distinction between the daily and the monthly hydro is that the scheduling period length. Daily means that the energy budget resets every 24 hours. Monthly means that it spans the full month. And monthly is more appropriate for larger reservoir systems with multi-month storage capacities. Region and transmission processing. So this builds the geographic backbone of the model. And this module creates two very important data sets for PRAS. The first is the region score, which is just the list of region names. And the second is region's load, which is the 8760 hourly demand matrix per region. Again, transmission lines within the regions are copper plated, so we don't really consider any transmission constraints, any reliability risks of lines within regions. On the transmission side, we process both individual lines and aggregated interfaces. So lines are point-to-point connection between two regions. and interfaces are just bundles of lines with the transfer, like total transfer limit between two regions. And lines also have their own failure rate and repair probability, and PRAS can stimulate transmission outages as well as generator outages. So for new transmission, we have a similar issue with new transmission, like we did with generation coming from copper, where the model outputs new transmission capacity, but leaves it up to us to either expand existing interties or add a new line between regions. So for this, we first add up the total new transmission coming from copper for each between each provinces. And then the linkage provides two different modes for the config to handle this future transmission expansion. The first is called new line mode. So in this mode, a new transmission line from the new transmission capacity from copper is created as a new interprovincial intertie. And the second option is called the distributed mode. So in this mode, the new transmission capacity is added to the existing interprovincial line between the same regions. So initially, we were modeling each node as its own region, which basically led to a lot of false precisions and was giving us unreliable results. So we decided to aggregate up. When you enable provincial aggregation in the config file in the linkage, the pipeline doesn't just collapse everything into a single node per province. It aggregates individual coders nodes into planning super zones, is what I like to call it, which are just sub-provincial clusters defined in a CSV file. So the algorithm runs in 4 steps. In step 1, we build the initial node to province or node to zone mapping from the coders data. And then the second one, we override that mapping using the super zone CSV, which assigns each node to a planning cluster. And then after that, those super zones have now become the new PRAS regions. So each zone's demand is the sum of all of its constituent node loads, and generators and storage and everything else is also remapped to their zone. Step 4 is the transmission. So lines where endpoints are inside the same super zone are dropped because interzonal transmission doesn't really matter for this model. And then the lines between different super zones are bundled into a single aggregated per zone pair interface. Failure probability for the bundle is taken as the maximum failure probability across all of the bundled lines, and the repair probability is taken as the minimum. The result is hundreds of individual nodes become a manageable set of regional clusters, while still trying to preserve the interregional transmission structure that PRAS needs. So how do we actually aggregate? So we saw that we need this aggregation, but there's hundreds of nodes, many of them closely tied together electrically, and treating each one separately can make the results noisy or misleading. So our clustering scripts ask a simpler questions. Where does the grid naturally split? So for this, we start off with the year of hourly transmission line utilization. So lines that are heavily loaded are bottlenecks. They're the weak links between different parts of the system. So we use that pattern to build a similarity matrix in which areas that are strongly connected and areas which are separated by congestion. Then we run a clustering algorithm that groups the regions together in a way that puts the bottlenecks between groups, not inside of them. The idea is that the areas on the same side of a congested interface behave more like one planning region, whereas areas on the opposite side should be modeled separately. Each superzone should be internally well connected, but separated from its neighbors by the lines that actually get stressed. So the end result is a mapping from every network node to a superzone level, which the main preprocessing pipeline uses to aggregate demand, generation, and transmission. into smaller but physically meaningful set of regions for the final PRAS run. And this slide shows us what it looks like visually. This shows us the geographic distribution of the superzones across the provinces, where nodes are colored by their planning cluster assignment. And you can see how hundreds of individual substations of the coders network collapse into like smaller sets of coherent planning regions. And the interzone connections that matter for adequacy purposes are still mostly preserved. So coming into some of the weather stuff, for climate and weather, the pipeline runs in two fundamentally different weather modes, controlled by, again, a flag in the config file. This extreme weather implementation is actually done by one of our other developers, Jonas, so shout out to him. In the baseline weather mode, we use the standard Mera year capacity factors as is and apply the outage rates from our constants.py file with some variations for the 2025 weather year. So these represent expected average operating conditions for the chosen weather year. And this is usually the reference case. In extreme or weather mode or climate weather mode, we apply region-specific multipliers to multiple parameters simultaneously. So both modes share the same foundation. The capacity expansion model future build out, what gets built, where it gets built, hourly wind, solar, hydro profiles, and transmission network. Like nothing in the grid design changes between the two modes. The difference is just an extra layer on top in extreme mode. So that layer is built offline by a separate weather impacts workflow, and it uses real historical weather plus synthetic hazard events, heat, drought, ice, wind, wildfire, to estimate regional stress. So these are computed outside of this linkage repo in the weather impacts project. And then those results get converted into hourly adjustment files, which is stored in a configurations folder, and that's applied at runtime when we build the PRAS inputs. A spatial mapping step ties each adjustment to the right region or transmission cluster, and every weather event behaves differently. Like for example, a heat wave only run might hit mostly generator capacity. Ice storm might hit mostly lines, or we might want to model risks that go across all parameters. I also want to highlight a significant data challenge that we've come across, and that is repair probability. The repair probability values, which determine how quickly a failed generator or failed line returns to service, has been extremely difficult to source for Canadian assets. So we're currently using generic values, not specific, like Canada-specific records. And this is one of the most significant sources of uncertainty that we have right now in the outage modeling. And it seems genuinely hard to improve without access to some kind of maintenance logs. So once all of this pre-processing modules have finished, we have intermediate text files, one per PRAS data group. The HTF5 converter takes all of those and packages them up into single binary files, the .pras file. And then this step is fairly mechanical, but it must be exact. PRAS is pretty strict about the schema. The converter handles the correct data types for each group. Some groups are integers, others are float. The required dimension ordering for each matrix is also strict. And alongside the HDF5 file, this pipeline also writes human readable debugging CSVs for every group. So you can open them in Excel to sanity check whether generators are correctly assigned to regions, whether hydro capacity factors look reasonable, demand profiles make sense before committing to a Julia simulation run. So this is the scenario configuration system, and it's what makes the pipeline so easy to run between scenarios. every single scenario is defined entirely by a YAML config file. The year, the provinces, data source, the path of the capacity output, expansion model outputs, transmission mode, how many Monte Carlo samples do we want, whether to apply climate multipliers, whether to aggregate regions, should we run EFC, ELCC. The power of this is that creating a new scenario is trivial. If you want to know what if we triple a specific interconnection, you just change your capacity expansion model outputs and then the new transmission mode fields and then run the pipeline. And all of this complexity of the pipeline is completely abstracted. You get a new .pras file and new reliability results in minutes and on a perfectly comparable basis to every other scenario. So after the simulation is complete, what do we actually get from PRAS? This gives us an overview of the key output files. Firstly, there's regional balance.txt. So this is just a quick sanity check that runs before the main simulation. It makes sure that each region has enough capacity to meet its own demand without considering transmission. It's just a good way to catch any major data input errors early on. Next, what we have is the hourly outages.csv. This is a very detailed file that gives you the expected megawatt shortfall for every single hour of the year for every single region that we're modeling. And this is where we can really dig in and identify the specific times of the year that are driving your reliability risk, what might be going wrong there. And then there's the hourly utilization.csv. This file tracks the utilization of each transmission interface for every hour. It's incredibly useful for identifying transmission bottlenecks and understanding how power is flowing across the system. Building on that, we also have congested interfaces.txt. This file just provides a summary of the interfaces with high utilization, typically over 80-90%. It gives you the average and the maximum utilization statistics and serves as it's a good starting point for identifying where transmission, the congestion is happening, where upgrades might be needed. And finally, we have the global metrics.txt. So this is your high-level summary. It gives you the key reliability indices for your system, LOLE, EUE, and this is the file that you look at to get to the big picture and see if you're meeting your overall reliability targets. For example, if suppose we run our simulation and finds that our LOLE is around the target threshold, great news. But then we notice that our EUE is surprisingly high. This tells us that while shortfalls aren't happening very often, when they do happen, they're severe. And the energy deficit is concentrated in just a few critical hours. So where do we go from there? First, we'd open up the hourly outages.csv file and look for those problem hours. We might find, for instance, that one particular hour shows a very large shortfall. And then the question becomes, is this a system-wide problem or is this just localized? So we'd look at the unserved energy by region for that hour. Let's say we discover that only region X has a non-zero EUE and all the other regions seem to be fine. This just immediately tells us that this is a localized demand issue and it's not a generation shortage across the system. Next, we check the hourly utilization.csv to see what's happening with the transmission interfaces feeding into the region X during that hour. If those utilizations are very close to 1, meaning that it's 100% loaded, that confirms our diagnosis. The neighboring regions have plenty of power available, but they just aren't able to send it to this region because the transmission lines are maxed out. At that point, we've identified both the problem and potential solutions. Transmission expansion into that region is the obvious fix. We might also consider local storage or something else in region X that can help shave that peak load and avoid that shortfall. This is exactly the kind of targeted insight that makes PRAS so valuable for planning. So we have a results dashboard, which is a web-based visualization tool built in standard HTML, CSS, JavaScript. However, we are working on a new dashboard in our idea tool that is to be released soon. the current dashboard reads the hourly outages CSV from the PRAS output folder and renders several views, a geographic map of shortfall magnitude, hourly time series plots, heat maps showing like which day has shortfalls, any patterns, summary tables. And this dashboard is great for anyone who needs to understand what the geographic and temporal distribution of risk looks like without needing to dig into the raw CSV files. And it makes the Monte Carlo results accessible and communicable to non-technical stakeholders. So this is a quick look on like how the map-based visualization looks like. You can see that the zones look more manageable than just having all of the buses and generators here. And you can also see that the congested lines here between different zones in red. So these are very preliminary results from a comparison scenario for Alberta and BC. The 2024 present day baseline shows close to zero loss of load, 0.01, I think, which is well within the industry adequacy threshold. But when we project forward to 2050 with the capacity expansion model built out and current interprovincial transmission capacity, the LOLE jumps up. The system is not seen as adequate under those assumptions. And then expanding the transmission brings the LOLE down and shows an improvement about 40%, which is decent. Again, I want to caveat that these numbers are very preliminary and heavily depend on the scenario setup. But it's just an example of how we might use the PRAS outputs, the PRAS dashboard for scenario comparison. This next chart shows us when shortfalls occur across the year for the 2050, the non-expanded transmission case. And this shows the hourly like UE in megawatts summed across all regions. So this actual R2R number is not really relevant. Rather, what we should be looking at are the trends. The pattern is very seasonal. Nearly all the shortfall events are clustered in winter, sharp spikes in January, February, and December. And those winter peaks correspond well with the cold weather stress peak heating demand, reduced solar, tighter margins from thermal and hydro. And from April through October, the system shows like near zero shortfall. So summer seasons are not the binding constraint in this particular run. For transmission and capacity planning, we know that, okay, we should be looking at winter adequacy instead. So for anyone who actually wants to run this pipeline, here's the steps for the setup. First, clone the repository from our GitLab, install Julia, set up the Python environment, activate it, and install all the requirements. Fourth, we also need to install a few Julia packages, PRAS, HDF5, data frame, CSV. All of this can be done with this like one-line command. And then copy the PRAS analysis script into the Julia package directory, and then run your scenario with the like main.py command. And that all that needs is a scenario name and the output folder. All you have to be careful is you're setting up the config file exactly like how you would like it to be. The full setup may take maybe 20 minutes the first time, and after that, running a new scenario is just, again, changing your capacity expansion model outputs, changing the config file, and then this one Python command. It's fairly easy to run. The pre-processing pipeline itself runs in about, I would say, depending on the size of the model, like 10 minutes on to anywhere from like 10 to 30 minutes. And then the Julia Monte Carlo simulation runs on top of that. These are a few resources for PRAS model, and then also the linkage repository, which might be helpful for anyone who wants to set up PRAS. And of course, like if you are having any problems setting either of them up, feel free to reach out to me. Yeah, thank you so much for all your time today. Really appreciate everybody being here. And our goal here is to make energy systems analysis more useful, more transparent, and easier to act on. If anything from today resonated with you, if you have a methodology question, data gap that you can help fill, or like a problem that you would like us to take a look at, we'd love to keep the conversation going. Feel free to reach out to us directly or like connect after the session. If you have any PRAS related questions, feel free to email me directly. That's my last email, pipasagoral@uvic.ca. And yeah, thank you again, and happy to take questions.
Amazing. Thank you, Bipasa. Very clear presentation. We got a lot of questions, so I'm going to read some of them and maybe you can answer as much as you can. That makes sense. So first question is from Matt Tierney. So in relation to node scaling, does that mean all of the nodes have the same pattern or time profile? So I don't know if you answer the question.
Are all of the nodes, the demand, is that in the same time profile? Is that what the question is asking?
Yeah, in relation to node scaling, does that mean that all of the nodes have the same pattern or time profile? So maybe, yeah.
Yeah, coming from either coders or the capacity expansion model, all of them are structured in a way that all of them have the same pattern. But for the PRAS one, if you're using a different capacity expansion model, those can easily be put into like the same format that we take.
Perfect. Another questions from Nathan Matos. So how many weather year do you simulate and do you create synthetic weather years?
So currently we're just doing one weather year, and hopefully in the future we might be able to simulate multiple weather years, but currently we're just doing one.
And there was a follow-up questions. Do you look at variability in hydro inflows? For instance, in Quebec can vary by 10 seconds of terawatt thousands of terawatt hour between years. So do you look at variability in hydro inflow?
So we do look at variability, but within the same year. We use capacity factor values, which change from R to R. So for that, we do look at differences in inflow, because I think it's the capacity multiplied by the capacity factor value, something like that, the equation goes.
I also want to add that we don't use multiple weather years by default for hydro or VRE, but the extreme weather kind of configurations that can be applied and that are by default stored in the repo that can be applied like to your own scenarios can simulate that by changing the failure probability of either VRE generators or hydro generators. There's also drought parameterization stored within that. So it's not done within the model explicitly, but the same kind of effect of multiple weather years can be simulated using the extreme weather parameterizations.
Thanks, Maddie. So following question by Norman Rousseau. So you include monthly hydro storage. What about multi-year?
Again, no multi-year, unfortunately, until now.
Until now, yeah.
Fingers crossed.
Okay, so the next question is from Patrick Burke. It's a long question, so unless you might want to read it, or maybe I'll try to read it. So when designing a model, for instance, for a provincial grid, what are the best practice for establishing sub-region? And what have you found provides the best result for utility scale planning? And then you mentioning for Alberta, there are 42 zones, which seems a high level of resolution. Will this be a reasonable level of resolution for similar or larger size province? And is zonal demand the limiting input for establishing those zones?
So currently what we're targeting is 8 to 10 zones for each of the regions, and maybe a slightly smaller number of zones for the smaller provinces. So what our aim is when aggregating those nodes into zones is that we're really keeping all of the congestion like accurately, because any provinces that are aggregated up, obviously the intra bus transmission doesn't really count. So which is why I've developed the spectral clustering that takes into mind, okay, how much is each transmission line congested? And we try to aggregate up in a way that still keeps that structure and still keeps that congestion in order to get more accurate results. And I agree, like 42 is a bit high. Like when we talked with Gart Stephen, the developer of PRAS, he said that like lower than that is ideal. So we've come up to like, again, 6 to 8, 8 to 10, somewhere around that number. And that's what we're using currently.
Thanks, Pipasa. There was a question also from Sophie Pellan. Why does PRAS accuracy get worse as the number of node increases? I think you mentioned that.
Yeah, I think it's just false precision for a lot. Just because we're modeling, like generator failure, line failure, and in normal circumstances, it's not like every single transmission line has this percentage of failure. So as we find that as we get down to the nodal level, the the discrepancy in each run when we make tiny changes seems to expand a lot. So which is why we decided to make the decision to aggregate up.
Got it. Another questions from Norman Musso. Is there a way to move bi-directionally between clusters and individual nodes if you find that one cluster is more active than expected?
I think if you're doing BC and then you have cluster level aggregation, I would imagine that in the same run, it is technically possible, but in the same run, if you have a cluster that is not treated as a cluster, but it's instead treated as a bunch of different regions, each node is a region, and while other clusters are like aggregated up, that might give you different reliability numbers, and that might be slightly skewed. So ideally you would want to do two separate runs, one with just cluster level aggregation and one maybe like nodal level in that particular cluster that you want to emphasize on.
Perfect. Another question, no name with this one, and maybe I think you've answered part of it already, but when aggregating into zones, why not use provincially defined transmission planning region where available? For instance, in Alberta and Saskatchewan. I think you mentioned that already.
Yeah, exactly. It's too many for our purposes.
Great. Following questions from Nathan. Have you done validation runs for each province? Meaning, have you verified that the loss of load metrics are reasonable using the base year quarter data, for instance?
Yeah. So we've mostly been focusing on Alberta and British Columbia until now. So for those, the numbers for the current 2024-2025 years have been looking good. So those have been partially verified for the but going into the future, of course, just because there is so much like it's all up in the air what could happen. Those are a bit harder to verify, say like 2050 numbers on their own, but we have been able to get like a good decent baseline scenario for the current one, and then hopefully assuming that all of the inputs and all of our coding and everything, all the model looks good, hopefully accurate results.
Yeah.
I also want to add that lots of the outputs are very sensitive to demand disaggregation. So with our baseline inputs, we feel we're as close as we can get based on the data publicly available, but can always be further refined going forward as data improves, or for your own use cases, if you have access to more granular demand data, that can hugely improve the accuracy of the results.
100%. I think demand data and the failure repair probability rates are where like our data side is a bit lacking. And then as those improve, hopefully our numbers change and improve as well.
Got it. Another question, I think you've mentioned it, but does the model currently incorporate US interties?
No, not currently. No, but that is in the plans and hopefully very soon.
Perfect. There was a couple of questions asked by Elizaveta on the expanded, not expanded, but Maddie provided a written answer. Questions by Michael Borg. Can PRAS be used to determine composite reliability? I'm not sure if you know what composite reliability, and maybe Michael, you can provide more information about the question, Michael, or we'll follow up with you. I believe you mentioned improvement to modify PRAS to accurately handle VRE in the model. Can you expand on the improvement you are working on?
Sorry, could you repeat that question?
Oh, sorry. Yeah, I think you mentioned improvement to modify PRAS to accurately handle VRE, right? In the model, VRE? variable? Yeah.
Yes.
Can you expand on the improvement we are working on? What are we trying to achieve with the VRE?
So with the VRE, if it's about the capacity factor that I mentioned, so again, we're using MERA level capacity factor, MERA data, and that the problem that we were facing were that like our coders data and the MERA data were not matching up on the grid cell, like they were not the exact same grid cell. So what we've basically done is just a matching algorithm of how far we want to go before we decide that, okay, this particular like capacity factor for this particular region is no longer relevant to the like the current grid that we're trying to, or the current generator that lives in that particular grid. Is that what we're talking about? I'm not sure if there's like anything that I didn't answer. I'm happy to expand on that.
Yeah, so Patrick might contact you about this later
Yeah,
because
100%.
I'm being conscious of the time, maybe 2 or 3 more questions. Could the model help to assess the risk of cascading failure? This is a question from Elizabeth.
We are not currently modeling cascading failure. We found that that has been a bit difficult to do, just given the data that we had. But I think given the correct data, or if you have that sort of data available, I think it is technically possible to do cascading failure. It's just not, we're not modeling that right now.
Got it.
I
So
think
Michael,
more
provide.
so
Go ahead.
with cascading failure, currently more so what we're assessing is like failure that's happening at the same moment due to similar weather impacts. You know, like if there is a heat wave in a region, that would be impacting similar generators within that region, not outside it at the same time, but not to the level of this generator fails, which means the other generators fail.
Exactly.
Yep.
Yeah.
Wonderful. Michael provided more information about composite reliability. It's about determining the adequacy of the generation system as well as the transmission adequacy together. So it's a combination of both. So I don't know if you want to comment on that, or again, maybe we'll follow up with Michael. So determining the adequacy of the generation system as well as the transmission adequacy together.
Okay, I think we are doing like transmission line failures, but the data we've had, again, it's a bit iffy on the failure probabilities. So even though we are modeling it, I wouldn't say how super reliable or accurate it is, but it's definitely in there.
Amazing. Thank you so much, Bipasa, for all those questions, this presentation. Thank you, Maddie, as well. So we are at the top of the time. So we'll be making those slides and recording available. So we'll send an email to the participant within a few days. In the meantime, again, feel free to contact us, to contact Bipasa if you have any question on that. Thank you again, Bipasa. Great presentation. Thank you, everybody, for attending this webinar. See you soon.
See you soon. Thank you all for being here.